Let's jump right into this explainer and talk about the absolute ultimate safeguard in the entire oil industry. I'm talking about the blowout preventer. If you've ever looked at a modern drilling rig and wondered exactly what keeps the unimaginable, crushing forces of the Earth safely in check, well, you're about to find out.
This machinery literally exists because of what used to happen without it. Just picture what the industry looked like before 1922. If a well found geological pressure that the crew wasn't expecting, the well would just empty itself into the sky. We're talking about a catastrophic, uncontrolled blowout roaring hundreds of feet up, taking the rig, and often the crew, right along with it. That terrifying reality is exactly why this equipment is the sole reason the modern industry is allowed to operate at all. It's not just some convenience, it is an absolute necessity. So here's our roadmap for today. We're going to start with why these things exist, then tear apart the anatomy of the stack, explore their absolute obsession with redundancy, look at the brutal testing limits, and finally, talk about the ultimate last resort.
Okay, kicking things off with why BOPs exist and how they harness extreme pressure. Let's look at why this is so much more than just a massive chunk of metal sitting quiet in the cellar of a rig.
Fundamentally, a blowout preventer, or a BOP, is a stacked arrangement of high-pressure valves installed right at the wellhead to prevent the uncontrolled escape of fluids. But here's the crucial thing you've got to remember. A BOP is never just a single switch or one solitary valve. It's a massive, meticulously layered system. When a well takes an unexpected influx of pressure, which is called a kick, the BOP's job is to hold the door shut. It buys the crew a closed, pressurized system to work inside so they can actually regain control.
Moving right along, let's actually look inside the stack and break down these layers of defense. This is some truly brilliant engineering, building from the top down. In practice, all this equipment is arranged vertically in a stack, and every single piece has a highly specific job. Up at the very top, you have the flexible annular preventer. Moving down, we hit the specialized ram preventers, stuff like your pipe rams and blind or shear rams. Sandwiched in between those is a drilling spool, which gives you the side outlets for the kill and choke lines. And this entire massive assembly rests directly on the heavy casing head. Now, the contrast between the top two lines of defense is super interesting. The annular preventer is incredibly adaptable. It uses a hydraulic piston to squeeze a massive rubber element closed, kind of like a camera iris. It can seal around pretty much anything, drill pipe, wire line, or it can even squeeze completely shut on an open hole. Because it handles odd sizes, it's the valve driller slam shut first to ask questions later. Pipe rams, on the other hand, are your hard, long-duration steel and rubber seals. But they aren't adaptable. They have fixed semicircular cutouts perfectly sized for one specific, known pipe diameter. Which brings us to the principle of redundancy. The idea of having 3 chances, not 1. Because honestly, no single seal can ever be fully trusted to hold back thousands of pounds of earth pressure on its own. This is perfectly identical to the logic used in aviation. Think about it. A commercial airliner doesn't just have one hydraulic system. It has 3 independent routes, so no single failure brings down the plane. A BOP stack is built on that exact same thinking. You get 3 chances. If the annular leaks, the pipe ram catches it. If that leaks, the shear ram steps in. And the redundancy isn't just physical. You can close the stack from the driller's console, from a remote panel near an escape route, or directly from the accumulator, which is basically an emergency battery of nitrogen pressurized fluid just for the BOPs. Now here's a huge misconception. The BOP itself doesn't actually kill the well. It's not a magic off switch. It just holds back the pressure. The sequence goes like this. You detect the kick, you shut in the BOP, and then you read the pressures. After that, you rely on totally different equipment, the choke manifold. You circulate the expanding gas out through the choke, while the mud engineer pumps heavier mud in to permanently neutralize the threat. So remember, it's a system. The BOP just holds the door shut, the choke manifold and the mud actually do the killing.
But look, none of this matters if you aren't testing the limits. Let's talk about proving the assumption. Because an untested piece of safety equipment isn't a barrier at all.
The numbers and regulations here are incredibly strict. Under API 53, BOP stacks, whether they're rated for 5,000, 10,000, or even 15,000 psi, have to undergo a mandatory pressure test at least every 21 days. Think about it. This equipment sits idle in the cellar for weeks doing absolutely nothing. The only thing that guarantees it's actually going to work is the last time you proved it worked. An untested BOP is just a really dangerous assumption.
But here's a really counterintuitive engineering rule for you. Before you test a valve at its massive high-pressure rating,
You actually have to do a low-pressure test between 250 and 350 psi first. Why on earth would we test something built to withstand immense, earth-shattering forces at such a tiny pressure?
It all comes down to how rubber behaves under force. High pressure physically energizes those rubber seals. It squashes them and forces them to grip super tight against the steel. Low pressure just doesn't have the muscle to do that. So a worn-out rubber seal might actually hold 10,000 psi perfectly fine because the pressure itself is forcing it shut, but it'll totally leak at 250 psi. High pressure hides a bad seal, making that low-pressure test the ultimate lie detector.
All right, finally, we reached the climax of the stack, the absolute edge case emergency protocol. Let's talk about the last resort, the ultimate trade-off.
I'm talking about the blind or shear ram. It's a phenomenal piece of engineering. When you hit this button, it doesn't just seal around the drill pipe, it brutally cuts clean through thick steel pipe and seals the entire wellbore shut. So if it's the absolute best, most definitive seal, you've got to ask, why wouldn't a driller just slam this one shut the second a kick is detected?
Well, it comes down to cost and physics. The catastrophic cost of shearing is massive. Once you hit that button, the drill string is severed instantly. You are literally dropping hundreds of thousands of pounds of steel straight to the bottom of the hole. You've instantly created a nightmare fishing job to retrieve all that pipe. Honestly, a lot of the time crews can't even get it back. They're forced to abandon that section and sidetrack the well entirely, bleeding hundreds of thousands of dollars in lost time and ruined equipment. You are purposefully sacrificing the string to save the well.
There's a saying in the industry that hits the nail on the head. It works, and it costs you the well as you knew it. It is a brutal, expensive trade-off. You only make that call when every single other alternative has failed or when human lives on the rig floor are in immediate danger. 3 chances, and this is definitively the last one.
So, to bring this whole thing together, the BOP is absolutely not a magic switch. From that highly flexible annular sitting up top, down through the specialized pipe rams, all the way to the final devastating cut of the shear ram, this equipment transforms a terrifying, unpredictable geological threat into a structured, manageable engineering problem. It relies on rigorous 21-day testing and aviation-grade redundancy to buy us the precious time needed to regain control.
Hopefully, this explainer completely changes how you view this seemingly quiet machinery. The next time you see a stack of heavy steel valves just sitting idly in a rig cellar, you'll know exactly what they're doing. It really makes you wonder just how much extreme volatile pressure is being perfectly managed right under our feet at this very moment. Thanks for hanging out with me for this one, and keep your curiosity flowing.